My name is Peng Huang, and I come from Zhejiang University. Thank you for having me here to present our work, InfoMasker, Preventing Eavesdropping Using Phoneme-Based Noise. This is a cooperative work with Yao Wei, Peng Chen, Zhong Jieba, Li Lu, Feng Lin, Fan Zhang, and Kui Ren. With the widespread of smart devices such as smartphones, laptops, and smart speakers, the user's voice privacy is seriously threatened. Attackers could use these microphones to keep eavesdropping on the users. To solve this problem, developers have proposed several solutions. Most operating systems will keep sending a notification when recording. Some even provide options to mute the microphone at system level. However, these solutions are far from mature for many reasons. The third-party operating system and camouflaged applications could still eavesdrop on the users. Besides, some legal recordings, such as those recorded by voice assistants, are not controlled by the users. Attackers can even place hidden recorders. So to prevent untrusted devices from eavesdropping on the user, we propose to deploy third-party hardware that can physically block most of the microphones in the environment so that the users can retain control of their own voice privacy. The scenario considered in this paper is shown in this figure. The user is surrounded by multiple recording devices that may or may not eavesdrop on the user's voice. The user places a jammer in the environment and turns it on when he does not want to be eavesdropped. The jammer can inject inaudible noise into surrounding microphones and make the recordings unrecognizable. In this scenario, the jammer should meet three requirements. First, the jammer should be effective to jam both human ear and ASR tools. Second, the injected noise should be robust to noise reduction methods. And third, the usage of the jammer should be user-friendly. It should not disturb the users in the environment. For this scenario, the jammer could be implemented with three types of signals. The first one is electromagnetic signal. This signal can disturb the circuit of the microphone and inject the noise into the recording. It is inaudible to human, but this method has very limited jamming range and may affect other electronic devices in the environment, such as pacemaker. The second one is adversary examples, which can disturb the ASR systems with small perturbation. However, this method can only fool a limited number of ASR system and is not working for human ear. The third one is to use ultrasound. This method leverages the nonlinearity of microphone. It is able to inject inaudible jamming noise without disturbing the users. Besides, this method has a reasonable jamming coverage, so it is the method that we choose in this paper. Now, let's first take a look at the principle of ultrasound jamming. In 2017, Dolphin Attack found that we can inject inaudible voice commands to microphone via ultrasound with the help of nonlinearity. As shown in this figure, assume the input of a microphone is ST. Because of the nonlinearity in the amplifier, the actual output will be the sum of ST and its higher order components. So in order to inject a target signal NT to the microphone, we can use two transmitters. One transmits the modulated signal and the other transmits the carrier. Then, because of the nonlinearity, the output of the signal will contain the target signal NT. However, there are two main challenges to jam microphones. The first one is in the ultrasound transmission. To effectively jam the audio recording, the energy of the noise should be high enough. For example, when jamming audio with white noise, to achieve a word error rate higher than 14%, the energy of the noise should be 3 times higher than the audio. However, the noise transmission energy cannot be too high, and otherwise the low frequency noise created by the transmitter can also be heard by the user. And the second challenge, which is the main one considered in this paper, is that both human ear and ASR systems have strong denoising abilities, which could remove many common noises easily, such as white noise, single frequency noise, and even other people's voice. For human ear, the auditory attention mechanism, which is also called the cocktail party effect, can filter out most noises, as shown in this figure. A person is in a noisy cocktail party. Although there are many people talking around him, he can quickly focus on the target people's voice, even under the interference of other noises. For ASR system, with the development of artificial intelligence, the noise reduction tools are also powerful, including speech enhancement and speech separation. The speech enhancement method can enhance the human voice components in the input signal and suppress the other noises. The speech separation method can separate the speech mixtures into two or more single voices. Although human ear and AI-based noise reduction are strong, they also rely on the difference between the noise and the target signal to separate them. This difference include the time domain differences and the frequency domain differences, which is listed in this table. Therefore, if we can design a type of noise which is similar to the speech regarding these aspects, it is likely to be difficult to remove by both human and ASR system. The normal jamming strategy, which is called energetical jamming, makes the speech unrecognizable by covering it, just like these two waves. However, because its jamming noise is irrelevant to the target speech, it needs high energy, or it would be easily removed. The second strategy is informational masking. Different from the energetic masking, it tries to disturb the speech instead of covering it. For example, if we insert the phoneme into the word desk, this word may be only recognized as disk. Compared to the energetic masking, it needs relatively low energy, as it does not need to completely cover the target. However, the effectiveness of the informational masking also relies on the similarity between the noise and the target speech. Otherwise, it could be removed by some powerful noise reduction method, such as human ear and speech separation. So to jam speech with informational masking strategy, we need to know some prior knowledge of the target signal. First, the structure of the target signal, human speech, is a continuous series of phonemes. And the second, the frequency domain properties, such as fundamental frequency and the timbre, are user-dependent and is relatively stable. While for the time domain properties, they are varying and uncertain in most scenarios. So the main idea of our noise design is to generate noise having similar structure and frequency domain properties to the target voice. Here is our noise design method. We first assume we have enough phoneme data with similar frequency domain properties to the users, and later we will introduce how we get this data. Our noise includes three parts. The first one is the accelerated continuous words. The reason for acceleration is to inject more words per unit time in the target signal. However, the rate cannot be too large, which will affect the timbre of the noise. We set the rate to 1.1 empirically to maximize the jamming effect. The second part of our noise is was concatenated with random rate and gap, which makes the noise more natural. The third part of our noise consists of continuous consonants, which is used to increase the diversity of the noise. So with this noise design method, now we present our system workflow, which mainly includes 4 parts: user registration, data augmentation, and noise generation and jamming. Now, we will dive into each part to show the details. First, in the user registration step, we aim to obtain enough phoneme data with similar timbre as the user. However, extracting data from the user's speech is impractical because recording a lot of audio from the user is time-consuming. So our method is to first recording the user's voice lasting a few seconds to extract the features using an autoencoder. Then we found speech samples in a public corpus, which is the most similar to the extracted feature, and generate noise based on them. Our experiments show that 5 seconds is enough for registration. In some cases, the amount of speech satisfying our requirement in a public corpus is insufficient. So we need to perform data augmentation while retaining the similarity to the target speech. According to previous work, modifying the emotional related part of speech signal has less impact on the timbre, which affects the similarity. So our method is to fine-tune the emotional related properties. We choose 4 emotional properties which vary within a reasonable range in a person's speech when spoken with different emotions. We determine the multiplication range according to our experiments. This figure shows the augmented data is still similar to the target speech, which is shown as the origin. So with the generated noise, now we need to transmit the noise to the air and jam the microphones. There are 2 main points in this part. First, we adopt the single sideband modulation instead of conventional double sideband to increase the limit of transmission energy. For the double sideband modulation, due to the nonlinearity, it will create a low frequency noise, the square of NT, which is audible to human being. While for the single sideband modulation, the modulated signal is NT times cosine 2 pi ft plus the hat NT sine 2 pi ft, where the hat means the Hilbert transform. Its frequency band will be half of the origin. The audible noise in this transmitter is square root 2 over 2 times the conventional situation. Our experiments also show that the single sideband method can increase the upper limit of the transmission energy. The second key point of noise transmission is pre-compensation. The recorded speech and jamming noise will experience different amplitude attenuation because acoustic hardware has different frequency responses within normal speech and ultrasound. We need to perform compensation to maintain the similarity level between these 2 signals. For normal recording, the distortion caused by the recorder could be represented by frequency response H1, while for the ultrasound jamming, the distortion caused by both the transmitter and the recorder, which could be represented by H2. So to eliminate this difference, we estimate H1 and H2 separately and pre-compensate the transmitted noise with this filter. And we have found that with pre-compensation, the injected noise will be more similar to the ideal signal as shown in this figure. So after explaining each part, here we show the system overview, again with details, including the user registration, data augmentation, and noise generation and noise transmission. Here is the hardware implementation of our system, which includes a transmitter array, 2 power amplifier, and a laptop. Our evaluation considers 7 types of speech recognition tools, including 4 commercial ASR, 2 open source ASR, and human beings. We mainly evaluate the effectiveness and the robustness of the noise. The effectiveness means if the noise can disturb the target speech significantly, and the robustness means if the noise can resist to several noise reduction methods. We first consider the effectiveness. The results show that all tested ASR system for all tested ASR systems, our noise can achieve a WER higher than 15% when the energy of the noise is equal to the target speech. And in the real-world scenario, our system also performed well. Compared to other existing jamming works, including one commercial device, our noise performs significantly better with the presence of noise reduction methods. In the real-world end-to-end scenario, where the user records 5 seconds of audio for registration and noise generation, our voice performed well in different distance and SNR settings. We then tested the robustness of our system against the speech enhancement and speech separation. For the speech enhancement, the result is interesting, that it will make the speech jammed by our noise harder to be recognized. We think the reason is that the method will enhance the energy of the phonemes, both from the speech and our noise. For speech separation, we train 3 different speech separation models targeting on separating 2, 3, and 4 speech series from the same person. And we found that compared to using speech signal as jamming noise directly, our noise is more robust, especially in low SNR scenarios. We also conduct a real-world case study in a normal office. We placed 4 transmitters in the room, and we found that most of the microphones in the room will be jammed. Here is a summary of our work. We propose a new type of noise based on the idea of informational masking. We conduct an in-depth study of ultrasound transmission method and then optimize several aspects to make it practical. Then the third one is we design and implement a system which is proved to have high effectiveness and high security in real-world scenarios. Oh, okay, thank you, and I'm happy to take your question.
Hi, thank you for your talk. So I want to know, if you use ultrasound for transmitting the actual jamming, how do you deal with an anti-aliasing microphone?
Sorry, do you mean that some microphone may be insensitive to the ultrasound?
So a anti-aliasing microphone uses either electronics or hardware design to cut out its ability to hit frequencies above some set threshold. So effectively, because you're relying on the aliasing properties of your ultrasound to move it down into the audible range for humans.
In practical, most of the microphone will be affected by the ultrasound because the nonlinearity takes place in the preamplifier of the microphone. The filter, the low pass filter and the AD converter is after the amplifier. So the previous work have proved that most of the either MAPS microphone or the other type or ECM microphone, all of them will be affected by microphone, will be affected by ultrasound, and all of them exhibits the nonlinearity.
Okay, thanks.